Hey guys, it's been a while since we had a video. I'm upstairs and my kids are sleeping, so I'm going to try not to talk too loud. I know I kind of get fired up when I'm talking about this sort of stuff, but I'm going to try and keep it down so I don't wake the kids up. We're going to start today looking at some more molecular geometry stuff, and this time, this step-by-step here is going to let you figure out kind of how to determine the geometry, and it's all based off of the table that you should have in your notes by now from last time. And then we'll get into something else, and I'll kind of skip a few slides when we get there. But first, and you can pause the video and write these down if you need to, but first we're going to draw the Lewis structure. And we kind of looked at Lewis structures last time and how they related to our geometry. Second, we need to look at the number of electron groups around the central atom. Okay, and so it's that central atom only that's going to determine the geometry of our structure. We don't really care about all of those terminal or outside atoms. We're looking at just the central atom. Then we can look at those electron groups and call them bonding or lone pair groups, and then we can figure out how many of each one we have, and based on number of electron groups, how many are bonding, how many are lone pairs, we can look at this table to figure out what our shape is, and it's all based on the Lewis structure. So having the Lewis structure correct is a big thing. Okay, also remember that if we have a double or a triple bond, it still only counts as one electron group. Don't need to write any of this, but I just want to talk about quickly how there is a way to represent three-dimensional structures on a two-dimensional paper. Okay, and so normally we have just this solid line here that indicates a bond, right? However, if we're drawing in 3 dimensions, this straight line indicates a bond that exists on the same plane as your paper or the board or whatever you're looking at. Okay, when you have a dashed wedge like that, that indicates a bond that is coming back behind what you're looking at, so back behind your paper or goes back through to the board. A solid wedge like this will come out away from the board or out towards you on your paper. So the three-dimensional structure of CH4 would have 2 bonds that exist in the same plane, and then 1 bond that comes out towards you, and then 1 bond that goes out away from the board. Okay, kind of looks like this, and you can see this is what I just drew, that tetrahedral shape where you have 2 bonds in the same plane and 1 going back and 1 coming forward, and then we have, other bonds or other arrangements that have that 3-dimensionality associated with it. Okay. No, we don't need to keep those. Let's skip ahead here. We're going to look now at molecular polarity. And so we've talked in the past about bond polarity, about how to determine whether or not a specific bond is polar. Basically today what you're going to do is look at all of the bonds within a molecule and determine if that will result in the entire molecule being polar. Okay, and so we know how to do this. We know the electronegativity difference, subtract the 2, and if the difference is between 0.4 and 2, that is a polar bond. Okay, and so this bond here between chlorine and hydrogen is a polar bond, and it results in the electrons being pulled more towards chlorine than hydrogen. Okay, and so that's what this little symbol is. It's called a dipole moment or a dipole symbol. And so it tells us that the electrons are going in this direction and that this side has a slightly positive charge. Okay, we're going to be using this dipole symbol a lot today. Okay, if we looked at, electron clouds, this is kind of what it looks like here, where we've got a high electron density over here around this one and a low one over here. Again, that's just the single bond. We can look at an entire molecule and look at each individual bond and determine polarity. Okay, so if we looked at the electronegativity numbers between carbon and oxygen, and I'm not entirely sure, but I want to say this is about 3.5 for each oxygen, and I think carbon is somewhere around 2.5. So if you subtract those, that's a difference of 1, which falls in that range of being a polar bond. Since the oxygens here are more electronegative, they get the arrow of the electrons going towards them. Okay, so each bond here, this one is polar going this way. This one is polar going this way. But if we imagine like a tug of war going on with these electrons, since they're both equally polar, there is no net movement of those electrons. So the result is a non-polar molecule. We would say that these two dipole moments cancel each other out. Okay, and so if we look in the molecule here, it's even. Those electrons are evenly distributed. Okay, so that results in a non-polar molecule. Now in something like water, where we have oxygen and hydrogen, that is also a polar bond. Those electrons are going towards oxygen. These bonds are not being pulled in opposite directions, right? Those electrons are all going towards the oxygen here. They're going this way. And so this is going to result in a polar molecule because these polar bonds don't cancel out. If we looked at our electron density over here, we have this molecule having a slightly negative charge on the oxygen side because those electrons are being pulled towards the oxygen atom via two polar bonds, one there and one there. Okay, if we added those together, it results in, let me erase all this, it results in this. Okay, and so there's a large movement of electrons towards the oxygen. All right. Go ahead and pause this. I do want you to write this all down. So pause it, please. I'll talk about it here right now. So in order to determine polarity, you need to draw the structure and look at the geometry. Okay, so the two things that we've talked about so far, draw structure and determine its geometry. Then we need to look at each individual bond within the molecule. Okay, that's what step 2 is. Look at each individual bond and determine which ones are polar. Okay, if none of the bonds are polar, then the molecule is not polar. That makes sense. If we have polar bonds, we should, it says draw a vector. If you've taken a physics class, you're familiar with vectors and vector addition. That's just this symbol here. Okay, so you're going to draw a vector, the dipole symbol, pointing towards the more electronegative atom. Okay, and here it says that the length of the vector should be proportional to the electronegativity difference. That means the more polar the bond, the bigger the arrow. So if there's a large polar bond, it should look like this. If that bond is only slightly polar, maybe it looks like that. Okay, bigger the polarity, bigger the arrow. Then we determine if those bonds, those polar bonds, are going to add together or cancel out. Okay, it's called summing the vectors or vector addition. If the vectors add to 0, it's nonpolar. If the vectors add to a net vector, then we have polarity. And I'm going to show you what I'm talking about here in just a sec. Let's look at this question though. So we've got a molecule that has 3 identical polar bonds in a trigonal planar molecular geometry. Is it polar? Okay, pause it, see if you can answer this by yourself. I'm going to explain it. So trigonal planar, we have a molecule that looks like this, right? Or in 3 dimensions, a triangular shape all in the same plane, okay? It says that there are 3 identical polar bonds. So this bond has a vector like that, this bond has a vector like that, this bond has a vector like that, okay? Is the molecule polar? If we were to add up all 3 of these vectors here, they're all pulling at the same strength in opposite directions. If we were to add all these together, there is no net movement of the electrons on this molecule. So the answer is going to be no. Okay, it is not a polar molecule. Let's look at vector addition here. If you've taken a physics class, you kind of know what I'm talking about. Okay, this example 1 here is adding 2 vectors in the same direction, all right, of the same magnitude. And so maybe this is a linear molecule where we have something bonded here, something bonded there, and something bonded there. And each of these bonds has the same polar magnitude, and they're both going that way. Okay, that would result in a resultant vector with a magnitude of 10. We take +5 and +5, add them together, and we would get 10. Okay, so that is adding up a vector. Here, we've got one vector going in this direction that's twice as big, one vector coming back this way that's half as big, and so the resultant vector is a quantity of 5 in that direction. Okay, so this would also be polar. Okay, but something like this, for example, example 3 here, we've got equal vector sizes going in opposite directions. So our tug of war, there's no movement. Okay, up here in example 2, if we have that tug of war, we have movement in this direction. Okay, here, there's no net movement. But we know that it's not always this easy in a molecular structure, right? So we can add in different angles and 3 dimensions and multiple vectors, right? And so if I have a vector like this, this is that trigonal planar that's all being pulled with identical polar bonds. This was the example that they used. Okay, and so then these 2 vectors add up to this, which is going to exactly cancel out this vector, so we have a net movement of 0. Okay, but then these 3 vectors do not cancel out. There is not an equal and opposite pull like we have down here in this one. Okay, so this resultant vector between A and B does not cancel out C here, and has another resultant vector. This would be polar. This would be nonpolar. Okay, so it's all about how those bonds are, where the bonds are located. Are they pulling opposite from each other, or is there some offset angle? And then are those individual bonds polar or nonpolar? Okay, and so here, these are the only examples that they give you in terms of geometry, but this is some examples here. So if we have 2 identical polar bonds, and so that's the key here, they have to be identical. If they're identical polar bonds on a linear molecule, it's nonpolar. Identical polar bonds in a bent molecule, this would be like water, it is polar. Identical polar bonds on a trigonal planar is nonpolar. Identical bonds on tetrahedral, also nonpolar. Identical bonds on trigonal pyramidal, that's going to give you a polar bond, a polar molecule. Okay, that's all we've got for today. Spend the rest of the time working on mastering. I think you should be able to get about half of it done based on what we've talked about so far. Okay, be good for the sub. I don't know who it is. Take care of yourselves. Keep on keeping on. See you guys.